So this video is going to be slightly shorter than the previous videos, which were pretty long. So we are talking about CPA security. That is where we stopped last time. We were just starting to say that the model that we are now interested in, which is better than multiple message security, is chosen plaintext attack security, right? So what is chosen plaintext attack security? So suppose you have user 1 who's sending messages to user 2. Okay. They're encrypting with some K, and given a message M, they can see the message being sent is C, which is encryption K of M, right? And the ciphertext gets sent, which is visible to the adversary A. However, this is the same as the picture before. In chosen plaintext attack, the adversary can also send a message M1 or M2 or how many ever messages that he wants, and gets them sent across that they see as C1 and C2, which are C1 is equal to encryption K of M1 and C2 is equal to encryption K of M2. Okay. Now we want to know if our security is if our system is still secure or not, and that seems a pretty bad way because our standard models definitely fail. Standard models definitely fail. Models we have seen so far will fail under this attack. How? Adversary A sends output sends messages M0, M1 and sees their ciphertext and sees their respective ciphertext. Right? Then A outputs M0, M1 as chosen messages for private key encryption API, whatever N, right? And the algorithm it uses is and sees their respective ciphertext C1, C0, C1. He can also know by sending them one by one which ciphertext is which, so that he has no problem, or he or she has no problem with it. Output B prime is equal to 0 if C is equal to C0. B prime is equal to 1 if C is equal to C1. Okay, and so they have perfect control over if my model is if my message is getting broken or not. Sorry, what am I saying? They can perfectly guess if the message is M0 or M1 in every single case, and hence my probability of experiment A pi when is equal to 1, probability is going to be 1, which is much bigger than 1/2, right? And so the question becomes, is this model too strong? my one-time pad, which seemed like a nice thing, completely fails under this attack. So is this model too strong? Is this threat model too strong? Too strong. And the answer is no, not really. In real life, there are many ways an attacker could influence the encryption. We have no idea. So in practice, there are many ways. There are many ways um, an attacker can influence. An attacker can influence what gets encrypted. Influence what gets encrypted. Okay. So we have no idea what is a good model. Like we have no idea. Okay, this is exactly how they are going to be influencing. In that case, you could predict how to deal with it. But if we have no idea how they're going to influence, we can't really say, oh, this is the best model. So not clear how best to model. How best to model. However, um, whatever type of attack A does, generally chosen plain text attack will encompass any such influence. So chosen plain text attack encompasses attacks encompass any such influence. Any such influence. Okay. Moreover, in cases, in historical cases and everything, there have been times when the attacker actually knew exactly what the message to send was. Moreover, in some cases, an attacker may have significant control. An attacker may have significant control. Significant control over what gets encrypted. Over what gets encrypted. For example, in World War II, the British planted mines in the in locations that they would know the Germans would find, and wait for those messages to be sent to the headquarters. That allowed to break, for example, one British in World War II. In World War II, British planted mines, uh, where Germans would find them, where Germans would find them, and they would look. They would what do you call? They would intercept the messages. They intercepted the encrypted messages. Let's see, encrypted messages being sent to the headquarters, sent to the headquarters. Okay, since they knew what they are looking for, the information that there are mines here, they were able to break these, thus able to break German encryption. Okay. Similarly, in another part, in the Battle of Midway, Battle of Midway Island, the U.S. intercepted some messages that the Japanese Navy had sent, saying that we need to that they plan to attack some target AF. U.S. intercepted messages of Japanese Navy and his Navy planning to attack AF, where AF was something that they could not completely decode. They had no idea of what exactly AF in that message was. However, they had suspicion that AF is the Midway Island by other methods. Suspected AF is Midway Island So this they sent a fake message that could be intercepted by Japanese. Sent fake message that Japanese could intercept. Reading Midway Island needs water. Midway Island needs supplies and mostly water. Needs water supplies. Okay. And then they intercepted the Japanese message. Intercepted the Japanese message reading AF low on water to confirm AF is equal to Midway Island. And they managed to put defenses in place for Midway Island, and they were able to stop the attack. Okay, so now that we have such a threat model, the idea is how do we set up an experiment? Because our standard experiment is definitely going to fail every single time. So, to pass every single time. So we need to do something slightly better. We can't just say, oh, encrypt it with this key, and it is a deterministic key. We need to do better. And so here's the experiment that we set up. Experiment for CPA security. Fix pi is equal to encryption. Generator, encryption, decryption, except this time encryption is by an encryption oracle. Okay, encryption is by an encryption oracle, or is that A has access to. Okay, so the encryption oracle, which is generally going to be written ENCK dot. Okay, and this is going to be randomized. Is randomized. Okay, so given the same key and the same message, it does not output the same C every single time. It's going to output a different C most of the times. Okay, so fix pi and adversary A actually. Define the randomized experiment. Define randomized randomized experiment private key encryption of CPA security A pi of n as follows. In the first step, my generator gives a key k from generator, which takes an input 1 to the n. Okay, so you tell it basically how big a key you want, and it outputs a key of that length. Okay, in the second step, adversary interacts, knowing 1 to the n, interacts with an encryption oracle. Encryption. We know what the encryption oracle is. With the encryption oracle, with encryption oracle enc dot, and then outputs messages, and then outputs messages m0 m1 of the same length, Okay, so now he has access to the messages, and they have access to he has access to the encryption algorithm, and he provides two messages. They provide messages. Now, in step 3, uniform bit B is chosen. It's chosen from 0, 1, and a ciphertext is then created. Ciphertext C is generated from encryption K of MB. Okay, and this is given to C. Give C to A. Okay, now A can still interact. A can still choose to interact with encryption oracle all this while, even after they have received the message. They don't. It doesn't matter. A can continue. A can continue to interact with with encryption key. And in the step 5, it has to guess which message it thinks it is. Outputs B prime. A succeeds if B is equal to B prime, and the experiment is evaluates to 1 in this case, and the experiment evaluates to 1 in this case. Okay, this is how we modify our algorithm, and our definition of CPA secure in that case is going to be definition. Pi is secure against chosen plain text attacks. Secure against chosen plain text attacks, which is denoted CPA secure, if for all PPT attackers A, there is a negligible function. There is a negligible function epsilon such that the probability of the experiment private key CPA E pi of security parameter n is succeeding is smaller than or equal to 1/2 plus epsilon of n. Okay? As before. So, as we discussed, it is impossible for deterministic encryption, as noted before. This is impossible for deterministic encryption. Encryption. Right? And so definitely our this thing has to be non-deterministic. Okay, so therefore encryption oracle has to be non-deterministic. Has to be non-deterministic. Okay, and what we can actually show is that if we modify our definition of CPA secure slightly to create a different type of attack, we can actually secure it for multiple encryptions. Is it secure for multiple encryptions? So the biggest flaw of security for multiple encryptions was if one of the columns had the same message and the other column had different messages, right? Uh, then if your same ciphertext is occurring twice, you could be sure that it's the column with the same messages. Now we can bypass that, since encryption K is not going to be outputting the same for both cases, right? So here's how we set up an experiment for multiple encryptions, multiple message encryptions. Okay. So in this case, rather than giving the attacker access to just what do you call encryption oracle, we give attacker access to a left-right oracle. Give attacker access to left or right oracle. Okay, which is generally denoted LRK, comma B. Okay, and what does it do? Which given input messages m0 comma m1 of the same length, it outputs computes C, which is encryption of K of MB, and returns C. Okay. So if B is equal to 0, receive encryption of M0. If B is equal to 1, I receive encryption of M1. If the person really wants access to the old oracle, they just can do MM, right? Encryption sorry, not encryption. LRKB of MM gives encryption K of M. So this oracle is better than just access to encryption K of M, encryption oracle. Okay, so the attacker, if they so desire, can now just sequentially query attacker A can sequentially query LRKB of M01 M11 LM0T, sorry, LRKB of M0T, M1T, given lists M01, M02, dot dot dot, M0T, and M11, M12, dot dot dot, M1T. So it's not a very significant improvement, okay, but it's a slight amount of improvement. So the left right experiment is set up as this: the LR Oracle experiment, private key encryption of LRCPA A pi of n is as devised as follows. In the first step, a key is generated by using key k generated by using the generator with input 1 to the n. Second step, uniform bit B is chosen. Uniform bit B is chosen. 0, 1, chosen. Okay. In the third step, the adversary is given access to adversary A given access to A1 to N, given access to LRKB dot dot as above. Okay, with the lists that they have created. The adversary creates the list M0, M1, okay, as per we have been doing so far. 4. The adversary outputs a bit B prime. The adversary outputs a bit B prime. And 5, the experiment is defined 1. Experiment succeeds if B is equal to B prime and is defined to be 1. Is defined to be 1. The output is defined to be 1. And output is defined to be 1. Okay. And once again, the private key encryption is said to be multiple key secure. Sorry. Multiple. Okay. Let me just write it down. Private key encryption. Private key encryption. Key encryption. Encryption scheme. Pi has indistinguishability under as indistinguishability under multiple, okay, as indistinguishable under indistinguishable multiple encryptions. Multiple encryptions under a chosen plain text attack, under a chosen plain text attack, or which we will refer to as CPA secure for multiple encryptions. CPA secure for multiple encryptions. Multiple encryptions. If for all PPT adversaries A, if for all PPT adversaries A, there is a function, there is a negligible function, epsilon, such that the probability of the experiment, private key experiment, LRCPA PA of pi comma a of n is equal to 1 is smaller than or equal to 1/2 plus epsilon of n. Okay, and then this is a major theorem that we are right now going to state without a proof, because the proof is in chapter 11. We are not going to do it right now, but we should know it. Theorem 3.24 in the book. It says any private key encryption, scheme, encryption scheme, which is CPA secure, which is CPA secure, is also CPA secure under multiple encryptions, for multiple encryptions. Okay, so right now we are not going to prove this, but what we are going to look at is how to construct CPA secure inscriptions. Okay. How to construct CPA secure encryptions. Okay. And for that, the first thing we are going to look at is pseudo-random functions. Okay, this is the major thing that we're looking at. And so what is a pseudo-random function? Is it a function which is basically distributing things uniformly, or what? So informally, a pseudo-random function, looks like a random function. Looks like a random function, i.e. uniform function. But if I'm talking about a uniform or a random function, the question becomes, in what space? What am I looking at? So the space of functions I'm looking at is space of functions will be denoted FUNCN, which is the set of all functions mapping 0, 1 to the n to 0, 1 to the n. All functions mapping 0, 1 to the n, 2, 0, 1 to the n. Okay, so that begs the question, how big exactly is func n? How big is func n? How big is funcn? Okay, so here's how we will write down func n. Okay, function n. Given any function in function n, you can write it as using can represent a function in funcn using n times 2 to the n bits. Okay, so any one function in function can be represented using n times 2 to the n bits. How do we do that? So make a table. So suppose I am doing it for n is equal to 2, n is equal to 2. I make a table of all the entries. So 0, 0, 0, 1, 1, 0, 1, 1, and I map it to something. So I'm mapping this to 0, 1, 1, 0, 1, 1, 0, 0, whatever, some function that it maps, right? The left-hand side is going sequentially. I know how it goes. I have some order well defined on the left-hand side. On the right-hand side of my table, these entries are n-bit entries, n-bit entries. Okay, and how many of them are there? 2 to the n of them. 2 to the n of them. Right? So I store this function as a string, uh, 0, 1, 1, 0, 1, 1, 0, 0. Then the length of this L is equal to 2 times 2 to the 2. Okay, and so each function is being represented by n times 2 to the n bits. Okay, and therefore the size of funcn is going to be 2 to the power n times 2 to the n. That is how big it's going to be, because every single function is going to be represented by every function is a string of length n times 2 to the n. Therefore, the total number of such things possible is 2 to the n times 2 to the n. Okay, that's how big this is. Okay, now what is a random function? Random function is a function that is chosen uniformly from funcn. Chosen uniformly from chosen uniformly f from funcn. Okay, or equivalently, instead of storing an entire string there, what we can do is for each x belonging to 0, 1 to the n, choose f of x uniformly in 0, 1 to the n. Okay. So what does this do? Basically, this is filling up as needed, right? Fill up the fill, i.e. fill up the table with uniform values, and can be done on the fly as values are needed. Can be done on the fly as values are needed. Okay. Keep in mind when we are discussing functions, you might have had some confusion. You are allowed to repeat a string here. The function does not need to be one-to-one. Everything can be mapped to the same thing. It doesn't matter. All four of these could have been mapped to 0, 1. Okay? The right-hand side of this table could be entirely just 0, 1, 0, 1, 0, 1, 0, 1, and that's also allowed. That's still a function. Is it a good function? Maybe not. We don't know. But that is a function. So a pseudo-random function looks like this, a random function. So pseudo-random function, random function, function looks like a random function. Okay, so as previously, it doesn't make sense to look at any fixed function being pseudo-random, right? Given a function, how do you say that this function is pseudo-random or not? You need some distribution over functions, right? Makes no sense. Makes no sense to talk about one function being pseudo-random, being pseudo-random, i.e. we need a distribution, i.e. need a distribution. Okay. And how do we get a distribution? How are we selecting some functions? We looked at keyed functions. Look at keyed functions. Okay. So what are keyed functions? Keyed functions. Well, a keyed function is a function f from, so let f be a function from 0, 1 to the n cross 0, 1 to the n 2, 0, 1 to the n. Okay. Be a deterministic, be an efficient, be an efficient deterministic algorithm. Okay. Define fk of x is equal to f of k comma x. Okay. The first input is called the key. The first input is called the key. Okay. Now, we assume that f is length preserving. Okay. Assume f is length preserving, which is to say fkx works only if defined only defined if k is equal to x, if length of k is equal to length of x, in which case we have fk of x is equal to size of k is equal to size of x. Okay? Now, choosing a uniform k, in 0, 1 to n, so choosing a uniform key is equivalent to choosing a function fk, equivalent to choosing the function fk from 0, 1 to n to 0, 1 to the n. Okay? What that means is, i.e., for fixed key length n, the algorithm f defines a distribution over the functions in Fn. Algorithm f defines a distribution over functions in func n. Okay? So now note that the number of functions in FUNC-N is the number of functions in FUNC-N is 2 to the n times 2 to the n, as we saw before. However, fk, all these functions, which is a subset for k belonging to 0, 1 to the n, is a subset of FUNC-N, whose size is number of such functions, the number of functions in fk, k belongs to 0, 1 to the n, is how many functions are possible for every as many keys as there are, and there are 2 to the n keys, so the number is 2 to the n. This is really tiny compared to FUNC-N. This is tiny fraction of FUNC-N. Okay? So a pseudo-random function, f is a pseudo-random function. So pseudo-random functions, PRFs f is a pseudo-random function, if fk, for a uniform key k, which is of length, we assume n, is indistinguishable from a uniformly chosen function f. From a uniform function f belonging to C n. Okay. Formally, for all PPT distinguishers D, formally for all probabilistic polynomial time distinguishers D, we should have that the probability of k being chosen from 0, 1 to the n being fed to fk and computed that the distinguisher evaluating to 1 here minus the probability of f being uniformly chosen from FUNC n FUNCn and the evaluating on this function is equal to 1 should be smaller than or equal to epsilon of n. Okay, standard definitions. And what it means is basically any probabilistic polynomial time distinguisher D should not be able to figure out if my function is chosen uniformly or it is chosen using some pseudo-random generator. Okay, some examples which are insecure, so it do not work. Example insecure are, for example, f of k comma x is always equal to 0 to the n. Right? So whatever you feed it, it's always going to give you 0 to the n. F of k comma x is equal to k. Third, f of k comma x is equal to k bitwise XOR sum x. All of these are insecure, okay, and these will not work, but these are examples of what f can be like. Okay, so let me stop here. This is just about the same length, I guess, but let's stop here. We'll continue next time.